Just a reminder, this is the directional derivative. It's equal to the gradient dotted with the vector u. And two things. Thing one, the direction of maximal increase is the gradient divided by its own magnitude. Or in other words, the direction of the gradient. Sorry, and I know I read the bottom part first because I was distracted. So the direction of the maximal increase is just whatever direction the gradient points in. And then the second part to remember is the rate of maximal increase is just the magnitude of the gradient. Cool. So if our function f of x, y is given by the natural log of 9x, it was 9x squared plus 8y squared. Is that correct?
Yes.
Cool. And we want to find the direction. Was it the direction or the rate? I mean, we can answer both really, but sure. So the direction of max increase at the point 2, 5, we're going to find the gradient at that point and then divide by its own magnitude. So let's see. The gradient of our function in general is the derivative, or I should say the vector of partial derivatives. So the derivative of the natural log of some stuff is going to be 1 over the stuff. So 1 over 9x squared plus 8y squared times the derivative of the stuff, which is, if it's the derivative with respect to x, 18x. Similarly, the derivative of this with respect to y is going to be 16y over 9x squared plus 8y squared. Kind of gross looking, but that's fine. Our gradient at the given point, 2, 5, we're just going to plug in 2 for x and 5 for y. So this is going to get a little bit gnarly, but I'm going to make it actually way, way easier with one little trick. So plugging in 2 for x and 5 for y, 18 times 2 is 36. I really don't even want to write the denominator actually, because I don't actually need to, but I'm going to anyway. The denominator here is, let's see, 9 times 4 plus 8 times 25 is 236. Right? 8 times 25, yes, 200. 9 times 4 is 36. So then over here, 16 times 5 is 80 over also 236. I don't remember if I said this in this class or not, but I'm going to say it again, even though I didn't, if I said before. So what I want to point out is this vector is terrible. And I really, really, really don't want to normalize it or divide it by its own magnitude. Here's what I want you to really see. So this vector, 36, 236, and 80, 236 is probably actually smaller than unit vector. If I had to, it might not be. Yeah, I think it's smaller than unit vector. Let's say it looks like that. There's my gradient of f. And here I'm going to draw next. Not to scale. Here's my 236 times the gradient of f. And you know what's notable about both those vectors? They point in the same direction. And so I want to point out that whether I'm going to normalize the gradient of f or whether I'm going to normalize 236 times it, either way, when I normalize two vectors that point in the same direction, they both give me the same unit vector. Because when you're finding the direction vector, aka the unit vector, it's the vector of length 1 that points in the direction you're already pointing in. I could even pick something else. If I want to like divide top and bottom by 4, I could say here's another vector pointing in the same direction, and 36 divided by 4 is 9, and 80 divided by 4 is 20. That vector also points in the same direction. And so we could normalize any of those. And again, when I say normalize, I mean just divide by its own magnitude to get the correct unit vector. So here are 3 correct answers. The worst correct answer is the original vector, 36, 236, 80, 236, divided by the square root of 36 over 236 squared plus 80 over 236 squared. God, that's a lot to type into WebWork. Or a better answer, the vector 3680 divided by the magnitude of that vector, square root of 36 squared plus 80 squared. Or even more nicely, the vector 920 divided by the square root of 9 squared plus 20 squared. All 3 of those answers are the same. We could even write this last one, right? I could, like, 9 squared is 81, 20 squared is 400. You could write this as 9 over the square root of 481, and the second coordinate is 20 over the square root of 481. But it is true, right? If you take all of any vectors that point in the same direction and you normalize any one of them, all of them have the same unit vector pointing in the same direction, which is really nice. So if you've got something that's terrible and fractional, get rid of the denominator and then normalize that. Or even pare it down to something that's a multiple of it and normalize that. Other questions about this or about anything, actually, really? Or actually, does that seem clear, or are there anything I can answer about what I've said here? Cool. All right. It's a useful trick, I think. Much nicer than doing all that. Let's look at finding maxima and minima. And hopefully also Lagrange multipliers. So you guys have a test on Wednesday, right? And this maxima and minima homework and Lagrange multiplier stuff is due. I don't remember when it's due. It's due the 24th, which is Tuesday, I think. Yeah. Okay. So I'll always get to see you one more time before that homework's due. So if we don't quite get to Lagrange multipliers today, it'd be good if we did, but we'll see what we can do. So let's see. So sorry, notes. Yes. So finding maxes and mins. So just like in 17a, when we tried to find a maximum or a minimum of a function by finding the places where the tangent lines had a slope of 0, the same idea or a similar idea is going to be true for functions of 2 variables, aka surfaces. We're going to look for places on surfaces where the tangent plane essentially has a slope of 0. Although what I should really say is the tangent plane is parallel to the xy plane or parallel to the floor. So like the top of this paraboloid is where the derivative in the y direction and the derivative in the x direction is 0. Or the bottom of the same sort of shape. I'm pretending like I can draw. At that point right there, the derivative in the y direction is 0. The derivative in the x direction is 0. Or even, and I'm not great at drawing the shape, but I'm gonna try my best anyway. So this is a downward opening paraboloid, this is an upward opening paraboloid. And then also you have this, oh, that's not my best. Good start. This shape, which is called a saddle. Which I've drawn, not as good as I often do, sorry. But this point right here is a minimum in one direction and a maximum in another direction. And it's literally called a saddle because it's shaped like a saddle, right? Like if you've ever seen a horse's saddle, or if you've ever been hiking and you've gone like up, and you kind of get to a place where you go over the hill, or you can turn right or left and go up to another kind of peak. That's also called a saddle. And that is definitely has a flat tangent plane. So that's the idea, is we're looking for a place where the derivative in the x direction and the derivative in the y direction is equal to 0. So at a critical point, like here or here or here, the tangent plane must be flat or horizontal. I don't know what the right word to use is there. Meaning that both the derivative in the x direction has to be 0 and the derivative in the y direction has to be 0. Or in other words, well, if you're setting both of the partials equal to 0, you're really setting the gradient equal to 0. So often you'll hear people say the way we find critical points is by setting the gradient equal to 0. But really, I would think of it more in the first way. You're just taking each of the partial derivatives and setting them equal to 0. So let's look at some examples. Let's say we have the following function of two variables. For f of x, y equal to x squared plus y squared minus 2x plus 4y plus 3. Let's find all the critical points. Okay, so I'm just going to take each partial derivative. So fx is 2x minus 2. Fy is 2y plus 4. And we're going to set each of those equal to 0. And then we're going to solve. So pretty straightforward. We're going to get 2x equal to 2, x equal to 1. And we're going to get 2y equal to negative 4. So y is equal to negative 2. All right. So here's an important question. How many, you can show me on your fingers, how many critical points do I have? Show me on your fingers. It's okay to be right or wrong. How many critical points do I have? Yes, I don't even want to show you on my fingers. I have one critical point. My critical point is the point 1, negative 2. Right? A point here meaning we need an x and a y coordinate. We need the place on the surface where both derivatives are 0 at the same time. We have one critical point. Now, sorry, let me keep notes in order here. And we'll go ahead and pass. But we want to also find out, is this a maximum or a minimum or a saddle point? So we also want to classify the critical point. The way we do this is by using what's called the second partials test. So you might have seen back in 17a that you could tell if a critical point was a relative max or relative minimum using the first derivative test, where you saw if like the function was increasing or then decreasing or decreasing and increasing. But there was also a second derivative test that said if the function was concave down, you had a relative maximum. And if the function was concave up, you had a relative minimum. We're going to use an analog of that test here. So here is what we're going to calculate. We're going to calculate this thing called capital D. Capital D stands for the determinant of a certain matrix. It's kind of like the determinant of the Jacobian matrix. It's just a slightly different matrix. It's the matrix of second partial derivatives. In fact, let's go ahead and write it out that way. It is the determinant of this 2x2 matrix. Fxx, Fxy, Fyx, Fyy. So it's like the derivative, this first row is you take the derivative with respect to x first, and then of that you do x here, y there. And then the second row, you do the derivative with respect to y first, and then you do then x, then y. You don't need to know this specifically. When you take the determinant of a matrix, it's just, sorry, I shouldn't, we've talked about determinants, right? Maybe not in this class. So let me back up. You should have talked about determinants in 17b. That is definitely something that was in 17b, and it's about to come back. So we should certainly talk about it anyway, because you're definitely going to be finding determinants of matrices, eigenvalues, eigenvectors very soon. So if you've forgotten about that, you should probably wait until after this first midterm to start practicing it. But after this first midterm, definitely try to remind, and we'll certainly do in this class as well, but remind yourself of those things, because we are definitely going to be using them a lot, especially finding eigenvalues. So this is going to equal the product of the diagonal entries, fxx times fyy, minus the product of the off diagonals. But I'll point out that for any function we're going to encounter, the mixed partial in one direction is the same as the mixed partial in the other order. So we usually write this as fxx times fyy minus fxy squared, since fyx is equal to fxy. We can just write it that way. All right, so let's do it. So looking at our function here, or looking at our partial derivatives, for this example, fxx is equal to 2. fyy is also equal to 2. And fxy or fyx is equal to 0. So when I calculate d, I get 2 times 2 minus 0 squared, which is equal to 4. So here's what happens. If d is positive, it means we either have a relative maximum or a relative minimum. Yes, but how do we know? So we know in this case, so if d is positive, what that really means is you have to do more work. So now we're going to check what fxx is. Fxx is positive for this example, right? It's equal to 2. And I'll remind you of the thing I was saying a little bit earlier. If you think about the second derivative talks about concavity. So what we're saying here is the second derivative with respect to x is positive. So the second derivative in that direction is telling us the function is concave up in that direction. So if the function is concave up, you don't have a maximum, you have a minimum. So we have a minimum at the point 1, -2. Apologies. Let's go ahead and clarify the rules here. So for a critical point, let's call it x naught, y naught. If d of x naught, y naught, which is equal to fxx times fyy minus fxy squared, evaluated at the point. So then you'll plug in x naught, y naught. So if d is positive, d is greater than 0, then you have to check one more thing. Oh, sorry, there's something in the chat here. How did you get 2, 2, and 0 for the fxx, fy? Oh, sure. So if you look back here for a second, so to find fxx, I'm just taking the second partial derivative with respect to x. So the first partial derivative with respect to x was 2x minus 2. And I take the derivative of that with respect to x, I'm going to get 2. Similarly, for fyy, fy was 2y plus 4. If I take the derivative of that with respect to y again, I'm going to get 2. And finally, for fxy, well, if I take the derivative of this with respect to y, there aren't any y's there. So the derivative of that, that is just a constant. So the derivative is going to be 0. That's what's happening there. So if d is positive, then you have to check one of the second partial derivatives. So if fxx is greater than 0, then we have a max. Sorry, oh my gosh, the min, I'm sorry. I said it so confidently and I was like, wait, I'm saying the wrong thing. We have a minimum because concave up. If your second derivative is positive, the thing is concave up. On the other hand, if the second derivative in one specific direction is negative, then we have a maximum because concave down. Now you might be wondering, can I check either fxx or fyy? And the answer is yes. Here's why. For this whole quantity to be positive, these two things have to have had the same sign. If these were opposite signs, then this would be negative, and a negative number minus a positive number is even more negative. So this can't be positive if fxx and fyy have opposite signs. Yeah. Because they're the same. Right. But I should, let me back up. If D is positive, then for sure you are guaranteed that fxx and fyy must have the same sign. So they're either both going to be positive or both going to be negative. So we only need to check one of them. On the other hand, if D is negative, then you're done. Then we have a saddle. And so what that kind of means, although it's not always specifically in these directions, it kind of means one direction is concave up and another direction is concave down. Say that one more time. Right, exactly. So it's a shape that's kind of like this. One way it's concave up, and the other direction it's concave down. That. So concave down this way, concave up that way. And that's all you have. There's nothing. So if D is negative, you're done. Saddle, end of story. And then finally, sadly, if D is 0, then you cannot make a conclusion based on this test. There are other things you can do, but it usually doesn't come up too much, if at all. So that's the whole deal. If you've got a function of two variables, you can find the critical points, and you can test to see if each critical point is either a maximum or a minimum or a saddle point by plugging them into this D thing. This determinant of the Hessian matrix is what that actually is. All right, let's look at a couple more examples. Let's look at, say, yeah, sure. This next example, which is also not particularly exciting, but it's fine. So let's say with this next function, we have that f of xy is equal to 2x squared minus y squared plus 4x plus 10y plus 3. Also, if you have the time and the interest, I recommend graphing these either on GeoGebra 3D. Actually, I just saw recently there's like a beta Desmos/3D, which I think is pretty great. So check that out. But graph these and actually like plot the point and see, oh yeah, it is a maximum, or oh yeah, it is a saddle point. It's nice to kind of actually visually see these things in addition to just someone telling you. So let's find the critical points. So fx is going to be 4x plus 4. Fy is going to be negative 2y plus 10. Set those both equal to 0. I get 4x equal to negative 4, so x equal to negative 1. I get y equal to positive 5. So my critical point is just, again, one point. negative 1 comma 5. Don't worry, they're going to get more complicated. Then we're going to calculate D. So again, I'm looking at to find my second partials by just looking at my first partials. So D is going to be fxx times fyy minus fxy squared. So fxx, if I take the partial of that with respect to x, I'm going to get 4. Fyy, if I take the partial of y with respect to the partial of y, I'm going to get negative 2. And again, for fxy or fyx, I'm still getting 0. These are not very exciting in that a lot of the time when you calculate D, then you're going to actually have to plug in your critical point to see if it's giving you a max or min. Here, there's nowhere to plug in an x or a y. D is just negative 8 all the time. Yeah, Johnson. Why is fxy 0? Good question. So here's fx. It's equal to 4x plus 4. If I take the derivative of that with respect to y, are there any y's? Right, exactly. So since that capital D is negative, what do we know we have at our critical point? Is it a max, a min, or a saddle? It's a saddle. So I want to remind everybody, because people often kind of miss this fact after a while. If D is positive, it means you have to check something else. So if D is positive, you can't just say you have a max or a min. You have to be like, oh, I need to do more work. It's kind of like when you had limits back in 17a and you got 0 over 0. You can't say anything yet. You have to do more work. Let's look at some more interesting examples. If I can turn the page here. Cool. Yeah, that's a good example. Let's say now we've got this function. F of xy is equal to x to the 4th plus y to the 4th minus 4xy plus 2. And we're going to do the same sort of thing. So fx is going to be 4x cubed minus 4y. I suppose if you were doing this kind of problem, you could start off by finding all the partials, like including the second partials if you really wanted to. I don't usually do it that way, but that doesn't mean you couldn't. And then the partial with respect to y is going to be 4y cubed minus 4x. Set those both equal to 0. Something to note here, which is noteworthy. These equations are symmetrical, meaning that if you interchange the role of x and y, you would get the other equation. If you replace x with y and y with x in this equation, you get that equation, and vice versa. And almost always when that happens, it means that all of your critical points are pairs where either x and y are the same, or if you get like 2 comma 5 as one point, you're also going to get 5 comma 2. Basically, every pair, its reverse also has to be a critical point because of the symmetric nature of our equations, which is kind of nice to know. So let's see. I'm going to try. Well, I can see one obvious solution. X and y are both 0. But that's not the only solution. Really, we have to be a little more careful here. I'm going to take this equation and solve for y. So I'm going to get 4x cubed equal to 4y, which is going to give me x cubed equal to y, or y equal to x cubed. And then I'm going to substitute that into the other equation. I might divide by 4 first, right? This equation I could rewrite as y cubed minus x equal to 0. And now I'm going to substitute in y equal to x cubed. When I do that, I'm going to get x cubed minus x equal to 0. Now, I'll tell you, it's almost always a bad idea to try and divide by a variable. I don't want to bring x over to the other side and then divide both sides by x. If I did that, just so you're all aware, this is going to be x to the 9th minus x equal to 0. If I brought the x over and divided both sides by x, I would lose x equal to 0 as a solution. So instead, let's just factor out an x. We've got x to the 8th minus 1 equal to 0. You could factor more. You don't really need to, I don't think. We can see that we're either going to get x equal to 0, or x equal to plus or minus 1. Technically, you could factor x to the 8th minus 1 a bunch more. Like is x to the 4th minus 1 times x to the 4th plus 1, and then x to the 4th minus 1 is x squared minus, right? It goes on and on, but you can see that 1 and negative 1 are going to be solutions here. So then if x is 0, y is going to be 0. If x is 1, y is also going to be 1. If x is negative 1, y is going to be negative 1 cubed, which is also negative 1. So these are my critical points. Now let's find D. So capital D. So I'm taking the second partials now. So the second partial with respect to x is going to be the derivative of this with respect to x, which is going to be 12x squared. My fyy is going to be 12y squared. And my fxy is going to be negative 4. Let me square it. And I would say most of the time, it's probably not in your interest to do a lot of simplifying for this. I wouldn't really care to write this out as 144x squared y squared plus 16. I could. I don't think you really need to. So let's see what's happening at each of these critical points. If we plug in 0, 0, I feel like I've made, let me just make sure I didn't make a dumb mistake here. No, I didn't make a mistake here. Oh, I did make a mistake. It's a small one. It's easy to miss. I wrote the one small wrong thing for D. It's supposed to be fx x fyy minus fxy squared. So let me show you how I knew I was making a mistake. I started plugging in 0, 0, and I was about to get 0 times 0. I'm not gonna write plus 16. But I would have gotten plus 16. And the problem there is my D would have been positive, but both fxx and fyy were 0, which meant I'm not getting that it's concave up or concave down, which means I can't tell it's a max or a min. That's what was making me think, oh, I probably made a mistake because you don't usually get D being positive and both of the fxx and fyy being 0. That just doesn't really happen. And it's because I should have had a minus sign here. Sorry, big minus sign. And now my D is equal to negative 16, which is negative, which means I have a saddle at 0, 0. So 0, 0 is a saddle point. Let's plug in 1, 1 and see what happens. So D of 1, 1 is going to be 12 times 1 times 12 times 1 minus 16. I don't really care what number that is equal to. And you shouldn't either. You should only care that it's positive. So you should just, if you get this, you should be like, I know that this number is way bigger than that number. That's positive. Another good reason to not multiply everything out, I've also got my fxx and my fyy still kind of separate from each other. So with my D being positive and having to check fxx or fyy, I can see that both fxx and fyy are also positive. So fxx being positive means we are concave which way? Concave up or concave down? So when the second derivative is positive, it means we're opening up, but it means we have a minimum. So that's why I like to say it that way. So we're saying all the things, but yeah, concave up means we're opening upwards, and then that means we have a bottom point, a minimum. So we definitely have a minimum at 1, 1. But again, I'll stress that's really a good reason for not multiplying the whole thing out, because it makes it easy to see if your fxx is positive or negative without like writing out more work. And then finally, D of negative 1, negative 1. 12 times negative 1 squared is still positive 12. Same deal there. So D is still positive, and each of my fxx and fyys are also still positive. So I also have a minimum at negative 1, negative 1. For the same reason, it's still concave up, right? fxx is still positive, so it's still a minimum at that point. I think this one looks kind of neat, so I'm gonna pull up GeoGebra 3D just so we can see what it looks like. I think it's kind of cool. If I can, let me Give me just 1 second here, sorry. So if I my graphs, where are my graphs? Why are they hiding from me? Sorry. Graphing. There's we'll use the Desmos one. Why not? So if we graph this here, yeah, okay. So I'm going to use z instead of f of x, y. You could probably use f of x, y. Z equals x to the 4th plus y to the 4th minus 4xy plus 2. It kind of looks like a pair of pants, like with the feet if you didn't have holes in the bottom of feet. But look, there's a minimum, and there's your saddle point. Kind of cool. Anyway, I think that's neat. It's kind of fun. Oh, can I even do that? Yeah, cool. Right on. Can I do that? Maybe. Sorry, everything's in the way. Yeah, Jazel. So after I found x equal to 0 and plus or minus 1, I took each of those points and I plugged them back into the easiest place I could, where I had y equal to x cubed. So usually once you've found what one thing is, you have the other thing in terms of the thing you just found. So you can plug back into that. It's not always super straightforward, but often it's not too terrible. Yeah. Often I will say, the finding of the critical points is actually the more challenging aspect of these maximizing and minimizing problems. Let me grab here. Let's see 1 second. Let me grab these other examples I have. Not what I want. Sorry, they're hiding from me. Here, sorry, 1 second. Darn it, there's like a bunch of great problems that I know I have somewhere and I've put them up myself. Oh, let's see. Okay, fine. Let me sure. Let's say we have. Let me look something up real quick, because the problem with is if you make these problems up on the fly, things do not turn out well. So let me just grab something real quick. I know what I want. I just don't have it with me. Sorry. There we go. It's probably in this pile here. I just, when you can never find the thing you actually really want when you need it. Cool. Let's look at this example. Let's say our function is x cubed plus y cubed minus 3x squared minus 3y squared minus 9x. And we're going to find and classify all the critical points. So step 1, take those partial derivatives. Fx is going to be 3x squared minus 6x minus 9. Set that equal to 0. Fy is going to be 3y squared minus 9y. Set that equal to 0. And now we're just going to solve both of them equal 0. So for both of these equations, I can divide each of them on both sides by 3, which will be easy. So let's rewrite this as x squared minus 2x minus 3 equal to 0. And this one as y squared minus 3y equal to 0. Unfortunately, both of these I can factor. So x squared minus 2x minus 3 factors as x minus 3 times x plus 1. And y squared minus 3y factors as y times y minus 3. So from this first equation, I get x equal to 3 or x equal to -1. From the second equation, I get y equal to 0 or y equal to 3. And let's list out all of our critical points. So our critical points, and I'm going to try and make a little table here. My critical points are, well, x can be 3 and y could be 0. Or x could be 3 and y could be 3. Or x could be -1 and y could be 0. Or x could be -1 and y could be 3. If we think about this for a second, if x is 3, this first equation will certainly be 0. If y is 0 or 3, the second equation will certainly be 0. So x can be 3 and y can be 0 or 3. Similarly, if x is -1, this whole first equation is equal to 0. And for the second equation to be 0, y could be 0 or 3. So x can be -1, y can be 0, or x can be -1, y can be 3. We're trying to write all the ways that both equations are simultaneously equal to 0. All right. Let's find D. D is going to be fxx, so that's going to be 6x minus 6 times fyy, which is going to be 6y minus 9. I feel like I made a small mistake. I did make a small mistake. It's not that bad, but notice how I take the derivative of 3x squared and got 6x. I take the derivative of 3y squared and got 9y. I should have gotten 6y from there to there. So it just goes to show it's really important to pay attention to what you're doing. So when I divide both sides by 3 here, I really should have a y squared minus 2y instead of a y squared minus 3y. It's not too bad. We caught it soon enough. It should be a y minus 2, which means we get y equal to 0 or y equal to 2. And luckily, it's easy to change a 3 into a 2 if you write hard enough. So that's going to be a 2 there instead of a 3. And a 2 there instead of a 3. Sorry about that. So our calculating our D, our fxx was 6x minus 6. Our fyy is 6y minus 6. And our fxy is 0. Okay. So let's calculate D of each of these things. So D of 3, 0 is going to be 18 minus 6 times 0 minus 6. I don't care what the number is. I just care what the sign is. Is this thing I'm calculating positive or negative? It's definitely negative. So that means we have a saddle at 3, 0. For the next one, if I plug in 3 for x and 2 for y, I'm going to get, let's see, so I'm still getting 18 minus 6 for x. I'm now getting 12 minus 6 for y, or I should say, I'm plugging in 2 for y and getting 12 minus 6. And 18 minus 6 times 12 minus 6 is positive. So now I go back and I look at either fxx or fyy. And either way, whichever one I look at, I see that those are each positive on their own, which means I have a max or a min. A minimum, because it's opening upwards. Concave up. Check these other 2 points. So -1 for x, 0 for y. I'm going to get D of -1, 0 equal to -6 minus 6 times 0 minus 6. That's a negative times a negative, which is positive. But now I just said I had a negative times a negative. That means my fxx is definitely negative. So I have a maximum. And finally, the last one, I plug in -1 for x and 2 for y. D of -1, 2 is going to be -6 minus 6. And times 12 minus 6. And the negative times the positive is negative. So I have a saddle. So sometimes your function of 2 variables has many critical points. Oh, this is chat. So you can check, yes. So if D is positive, then you have to see if it's a maximum, and you can check either fxx or fyy. You don't have to check both, because in the cases where D is positive, fxx and fyy have to have the same sign. So checking that fxx is positive here is equivalent to checking that fyy is positive there. Same deal over here. Since D is positive, fxx and fyy both have the same sign, in this case, both negative. On the other hand, when we have saddles, it is often, although it doesn't have to be the case, but it's often the case that fxx and fyy are opposite signs, like here and like here. Which is why, and we don't have to bother with them, because we don't need to do that if D is negative. Cool. Other questions? Yeah. Finding the absolute maximum or minimum on a closed boundary. Yeah. Cool. That's exactly what I was going to do next. So let me just show you this picture instead of trying to draw it myself, because I'll be faster. So the idea, so it's finding the absolute max or absolute minimum on a closed boundary is kind of like in 17a when you found the absolute max or the absolute minimum function on a closed interval. So you've got some endpoints next. We have a lot more endpoints now. So let's pretend like we were trying to, let me just cover this up for a second here. We were trying to maximize and minimize, or find the absolute maximum. And you don't need to write this one down because we're not going to necessarily do this one, of this function on this region. So here's the point I want to make before we do this problem. On this region, x between -1 and 1, y between -1 and 1, which looks like a square, I'm going to imagine that square is like the floor of my house. And the roof of my house is the surface. And the roof of my house might look like that, where the absolute maximum is somewhere in the middle. And the absolute minimum, actually, all of the edges give me an absolute minimum here. It's kind of annoying. You can have more than one absolute minimum. Here, this one would actually have an infinite number of absolute minima, because each point on all 4 edges is an absolute minimum. Sometimes that happens. But your surface or your roof might also look like that, where up here in that corner, you have an absolute maximum. And over there in that corner, you have an absolute minimum. And it's sloping like upward this way and upward that way and upward that way and upward that way. So sometimes the corners are where you have absolute maxima. Sometimes somewhere in the middle is where you have absolute maxima. Or sometimes somewhere in the middle of a boundary edge is where you have an absolute maxima or an absolute minima. So essentially, there are 3 types of critical points we have to look for here. We have to look for critical points in the boundary, like in the middle. We have to look at any corners of our boundary, and we have to look at each edge of our boundary and see where that might have a maximum or a minimum as well. It's kind of a lot to check, actually. It's not always super duper fun, but it is something that we have to do sometimes. So let's go ahead and look at, yeah, let's, I don't love this first example. So let's go ahead and look at a different, I guess, no, we'll start with this first example. It's fine. It's a fine example. Sure. So sorry if I led you astray and thinking you shouldn't write it down. I apologize. So let me see if I've got something slightly different here. No, of course. No, okay. Yeah, fine. We can do this example. So let's say we've got this function equal to x squared plus y squared plus x squared times y plus 4. And it's on the 2 by 2 square, typically written as d equal to x comma y, such that x is between -1 and 1, y is between -1 and 1. And you don't have to, but it's often not a bad idea to draw the boundary in the xy plane. So in the xy plane, or I should say the region of the boundary, apologize. So 1, -1, 1, -1. So here's my boundary, my region in the boundary. The square where x and y both go from -1 to 1. And we know for sure we're always going to have to check any corner point. So automatically, I'm just going to label those. All the corners are always potential absolute maxima or minima. But first off, we're going to start by just finding the critical points in the usual way. So step one, find critical points. So take my partial derivatives. It's going to be 2x plus 2xy. And fy is going to be 2y plus x squared. Set them both equal to 0. And if you're not, so here's a case where it's not super clear which one I should work with first. If I tried working with the second one first, the best I could really do is solve for y. I can get y equal to x squared over 2. If I work with the other one first, though, I can actually do, I think, a better job. So try to work with the equation that is easier to work with. It's not always clear which one that is. But in this first equation, what can I factor out from both of those pieces there? I can factor out the 2x. I'm left with a 1 plus y. So I'm going to get either x equal to 0 or y equal to -1. I want to be super duper extra clear. 0, -1 is not a critical point. If you plug in 0 and -1 for x and y, the partial with respect to x is 0. If you plug in 0 for x and -1 for y here, what do you get if you plug in 0 for x and -1 for y in the second partial in the fy? -1 for y, 0 for x. I think I'm going to get -2. So just be careful, right? Just because this first equation gives us an x and a y value doesn't mean that both of those together create a critical point. We have to have both equations equal to 0 at the same time. But now what we can do is we can plug in either one of these to the second equation. So in the second equation, if I set x equal to 0, then I get 2y plus 0 equal to 0. So I get y equal to 0. So I end up with 0, 0 is a critical point. Similarly, if I set y equal to -1, well, then I get 2 times -1 plus x squared equal to 0. Adding 2 to both sides, I get x squared equal to 2. I get x equal to plus or minus the square root of 2. Check something out here before I say something dumb. Yeah, cool. Great. This is a really good example, actually. So I'm going to write something that's wrong, and then we'll say why it's wrong. So y is -1, x is plus or minus √2. So I get √2, -1, and -√2, -1. And generally, if this was just to find where this function has a maximum or a minimum, those would be critical points. But here, we're not going to use those because they're outside of the region. √2 is about 1.4. So this point I'm looking at is like, I've kind of drawn something in the way, but like it's right about here and here. That's -√2, -1, and that's positive √2, -1. I only want to consider points that are inside my region. So anything that is outside of the region is no good. All right, the second thing we have to do, which is a little bit more tedious, is to check out each boundary. So let's start with this line up here, y equal to 1. So along the line y equal to 1, what we do is we actually just go back to our function and set all of the y's equal to 1. So watch for a second. F of x comma 1 is going to be x squared plus 1 plus x squared times 1 plus 4, which we should simplify. That's going to be 2x squared plus 5. And now I'm going to find the critical point along that line where y isn't changing by setting the partial with respect to x equal to 0. So fx is going to, let me see. Yeah. Fx of x comma 1 is going to be 4x. We set that equal to 0, I get x equal to 0. So a critical point along this border is the point 0 comma what? What's the y coordinate have to be? It's got to be 1, right? I started off by saying y is equal to 1. I'm looking at this boundary here. So 0, 1 is also a critical point. And then we do the same thing for every other boundary. So we also do it for y equal to -1. I can fit that in here. For y equal to -1, same idea. F of x comma -1 is going to give me x squared plus -1 squared is still 1. But now x squared times y is x squared times -1. So f of x comma -1 is equal to 5. And if I take the derivative of that, it's 0 all the time. So what we're really saying there is along this boundary, the function's constant, right? No matter what, whether I'm over here or somewhere in between, the function is going to equal 5. I literally, right, that's what we've got right there. So if along a boundary the function is equal to a constant, you don't have to worry about that because we're just going to check the corners. And if they happen to both be minimums, then we'll say, okay, well, then the whole line across is also a minimum. But that's usually not going to happen, so I wouldn't worry too much about it. Let's check the other boundaries. We're also going to check, and I'm kind of losing my spot here. We're also going to check x equal to 1. So checking x equal to 1, we've got, well, f of 1 comma y is 1 plus y squared plus 1 times y plus 4, which is equal to y squared plus y plus 5. We take the partial derivative of that with respect to y. I'm going to get 2y plus 1. So that's equal to 0. We're going to get y equal to -1/2. So x being 1 and y being -1/2 is also a critical point. And then lastly, if we set x equal to -1 along our left-hand boundary over here, we're going to get f of -1 comma y. Plugging in -1 for x, we're still going to get 1 plus y squared plus 1 times y plus 4. I would note that's exactly the same equation that we have up here. So we're going to get the same value for y when we take the partial derivative. My fy of -1 comma y is also going to be 2y plus 1. Set that equal to 0. We're also going to get y equal to -1/2. So -1, -1/2 is also a critical point. We found them all. Now we have to test them all. So let's list our critical points. Our critical points are, I'm going to list the first, I'm going to list them in order. So I found, what was it? What was my first one? 0, 0. And then I got 0, 1. Then I didn't get 1. And then I got the ones I just got here, which are 1, -1/2, -1, -1/2. And then, of course, all the corners. 1, 1, 1, -1, -1, 1, and -1, -1. And then, just like when we found absolute maxima and minima in 17a, where you find all your critical points, and then you plug them into the function, the original function, to see which one gives you the biggest value and which one gives you the smallest value, the same process is true here. We're going to plug each of these 8 critical points into the original function. The original f of xy equal to x squared plus y squared plus x squared y plus 4. And we're going to see which of those gives us the biggest value and which of those gives us the smallest. So f of 0, 0 is going to be 0 plus 0 plus 0 plus 4. F of 0, 1 is going to be 1 plus 0 plus 0 plus 4. F of, okay, 1, -1/2, a little more work. Let's see, I'm going to get 1 plus 1/4 plus 1 times -1/2 is -1/2 plus 4. 4 plus 1 is 5. Add 1/4, you get 5 1/4. Subtract 1/2, you get 4 3/4. F of -1, -1/2, I believe is going to be the same. You're going to get 1 plus 1/4 plus a 1 times a negative 1/2 plus 4, and that's also the same. All right. Plugging in the corners now. I will point out all of my instances of x are x squared. So if I just change x from +1 to -1 and leave everything else the same, it won't change the value I get. Meaning, when I find f of 1, 1 and get 1 plus 1 plus 1 plus 4, which is 7, the same would be true if I did f of -1, 1, because all the x squareds are still going to be +1. And we get 1 plus 1 plus 1 times 1 plus 4. So I could have just skipped doing that work. Let's check the last two. F of -1, oh, sorry, I just did that one. +1, -1 is going to be 1 plus 1 plus 1 times -1 plus 4, which is going to be 5. And similarly, f of -1, -1 is also going to be 5. And then you just have to figure out which one's the biggest and which one's the smallest. So it looks like 4 is the smallest. It looks like these two are both the biggest. So we would then conclude that we have an absolute minimum at the point 0, 0 with a value of 4. Depending on how the question's asked, right? Sometimes they ask you, where is the minimum? Sometimes they ask you, what is the minimum? So the minimum occurs at the point 0, 0. It is equal to a value of 4. On the other hand, we have an absolute maximum at two different places. We have an absolute maximum both at 1, 1 and -1, 1 with a value of 7. Kind of a gross problem, but they're pretty doable if you just kind of follow the pattern. I feel like we should do one more because they're kind of off. And you're not always going to have a nice square as your region that you're trying to maximize and minimize over. So let's look. Yeah, I got time. Oh yeah, we got 15 more minutes. We got so much time. So much time. Let's look at another example here. You're very welcome. Yeah. So let's look at this next example. And I don't think we're going to get to Lagrange today, so we'll have to talk about Lagrange on Tuesday. So, yeah. Again, find the absolute maxima and minima of f of x, y equal to, you know what? This example I do not love. Let me grab something else just because this one just is not that interesting. Always a challenge. Sorry. One moment, please. Much better. Yeah. Cool. All right. So let's say we want to find the absolute maximum minimum of this function, f of xy equal to 3 plus xy minus x minus 2y on the triangular region. On the triangular region. With vertices 0, 0, 0, 5, and 5, 0. And I would, on a problem like this, always start off by drawing my region. So here's my region. My triangle has corners 0, 0, 5, 0, and 0, 5. Let's go ahead and find just regular critical points. Also, we already know 3 points we're going to have to check. 0, 0, 0, 5, and 5, 0. Right? Corners are always part of the equation. So critical points. Partial with respect to x is going to be y minus 1. Set that equal to 0. Easy to solve. You get y equal to 1. Other partial fy is going to be x minus 2. Again, not too terrible to solve. So my one quote unquote normal critical point here is 2, 1, which certainly is in the region that we're looking at. Not that you have to draw it in the region, but it's good to at least think about, is the point inside the region or not? Okay, now we're looking at the boundaries. So I'm going to look at this first one, this bottom boundary, which is y equal to 0. For y equal to 0, I'm literally just taking my function and replacing y with 0. So f of x comma 0 is going to be 3 plus 0 minus x minus 0. So it's equal to 3 minus x. If I take the partial derivative of that, I'm going to get negative 1, which means I don't have any critical points along that boundary. Or in other words, no, that's actually not a good way to say that, James. I take that back. Yeah. In fact, no, that's not okay. Cool. All right. I thought I said something totally wrong before. I did not. Just yeah. Cool. So what I will say is this: since this derivative is negative 1, basically it means if you go in the x direction, the function is getting smaller, smaller, smaller. So along this line, this point at 0, 0 should be as high as possible, and this point at 5, 0 should be as low as possible. Because as you go from left to right, the function is getting smaller, smaller, smaller along that boundary. Let's look at the x equals 0 boundary, which is also probably not exciting. F of 0 comma y is going to be 3 plus 0 plus 0 minus 2y. And again, if you take the derivative of that with respect to y, you're just going to get negative 2. So again, if you go in the positive y direction, the function's also decreasing, decreasing, decreasing. So it's looking like this might be the highest point, at least in that direction or that direction. Maybe not in that direction. It's hard to say. And then finally, we have one more boundary to consider. And often when you have something like a triangle, so for squares or rectangles, it's easy. The vertical boundaries are just x equals something, x equals something. The horizontal boundaries are y equals something, y equals something. Constants. Here, this third boundary is actually an equation of a line we have to solve, which is not terrible. Sometimes it's harder than others. But here we can see, I think without too much effort, that this is the line y equal to 5 minus x. If x is 0, y is 5. If x is 5, y is 0. So then I'm going to plug that in. So watch this. We're going to now find f of x comma y. But y is 5 minus x. So I'm just going to plug that in for y. So I'm going to get 3 plus x times 5 minus x minus 2 times 5 minus x. And before I take the derivative of this, I should simplify. So that's going to be 3 plus 5x minus x squared minus x minus 10 plus 2x, which is really, let's see. I've got a negative x squared. I've got a 5x minus x is 4x plus 2x is 6x. And I have a 3 minus 10, which is negative 7. And then the partial derivative here is going to be negative 2x plus 6. If I set that equal to 0, I'm going to get x equal to 3. And if I plug that back in, well, I'm along the line y equals 5 minus x. So if x equals 3, y is going to have to equal 5 minus 3, which is 2. Something at the point 3, 2. So the good news here is that I have less critical points to check. I only have 1, 2, 3, 4, 5. All the corners, the 1 point in the middle of the region, and then the 1 point on one of the boundaries. And of course, I'm out of room here, so we'll go to a new page of paper. Yeah. So we're just going to take our 5 critical points. We're going to plug all of them into the function 3 plus x times y minus x minus 2y. So first plugging in 0, 0. I get 3 plus 0 minus 0 minus 0. Plugging in, let's see, I'm gonna start with the corners because the corners are easy to see. F of 0, 5, I'm gonna get 3 plus, if x is 0, I get 0 minus 0, and then minus 2 times 5 is minus 10. Let's do f of 5, 0. So I'm gonna get 3 plus 5 times 0 is 0, minus 5 minus 0, it's gonna be negative 2. And then for my more interesting critical points, which were 2, 1, and 3, 2. F of 2, 1 is going to be 3 plus 2 times 1 minus 2 times 1, which is 5 minus 4, which is 1. F of 3, 2 is going to be 3 plus 3 times 2 minus 3 minus 2 times 2. That's going to be 3 plus 6 minus 3 minus 4. It's looking like 2. And now we just have to look at these numbers and see which is the biggest. It looks like it's 3. So again, be careful how you answer this question. I would say the maximum value is f of 0, 0 equal to 3. The maximum value occurs at the point 0, 0. Same deal over here for the minimum. The minimum value is negative 7. So f of 0, 5 equal to negative 7. The minimum value occurs at 0, 5. Yeah. I really wish we had more time. I would love to talk about Lagrange multipliers, which I will say is often not a topic that is covered in this class, but clearly it's being asked on your homework, so we should talk about it. But I guess it doesn't really do us any good to say they don't do it all the time. But what to say in the last 5 minutes here? Ooh, I know what to say. So we'll do an example that we'll then do again using Lagrange multipliers on Tuesday, so that we can kind of see how you can do something one of two ways. Let's look at the following example. Let's say I wanted to, sure. So here is a more kind of optimization problem. So we want to construct an open top box using, sure, 48 square inches of material to contain as much volume as possible. And I probably haven't written this in the most linguistically correct way. What I'm trying to say here, with maybe not the best words, is I have essentially 48 square inches of surface area to work with. I'm going to make a box that doesn't have a top. And what I want to achieve is that that box can hold the largest amount of volume, or in other words, maximize the volume of this box. So let's draw a picture. Here is my open top box. And I'm going to label all the sides. And no one said anything about anything, so I'm just saying I'm going to call this side X, this side Y, and this side Z. And typically, when I'm trying to write an equation for things, there are two equations I need when I'm trying to optimize something. I need the thing I'm trying to maximize or minimize, which in this case is the volume. So I'm trying to maximize volume, which is equal to x times y times z. And then we usually have some constraining piece of information. We are limited by the fact that we only have 48 square inches of surface area to work with. So our constraint is that the area is equal to 48. But we can write an equation for the area here. The area is just all of the side areas added up together. So the bottom area would be x times y. This front face here would be x times z. That back face there would also be x times z. So I really have 2 times x times z. This right face here would be y times z. And the left face over here would also be y times z. I really have 2 times y times z. So I have 5 sides altogether, right? The bottom, the front, the back, the left, and the right, but not the top. So that should equal 48. So now what we're going to do is we're going to isolate one of these variables. And usually it's in our interest to pick z because we're used to working with functions of x and y. So I'm going to isolate z. So just watch for a second. I'm going to leave these two things on the same side. So I'm going to have 2x times z plus 2y times z equal to 48 minus xy. Factor out a z. So z equal to 2x times 2x plus 2y equals 48 minus xy. And then divide those things by 2x plus 2y. So z equals 48 minus xy divided by 2x plus 2y. The point is that now we can take this thing we found z equal to and plug it back into the thing we're trying to maximize. So now we're trying to maximize volume as a function of 2 variables. It's going to equal x times y times 48 minus xy over 2x plus 2y. And what I'll point out here, because I probably should stop talking because it's like 1:29 and 48 seconds. We just talked about how to maximize functions of 2 variables. You take both partial derivatives, you set them equal to 0, you find the critical point, and then you test that critical point in the d equal to fxx times fyy minus fxy squared. So we have the process already for dealing with this. It's not pretty, like this is still going to be kind of gross, but finding the critical points here is not too terrible. And I would love to do it, but I should actually stop because class is actually over. Which is too bad. I will mention here, if you do this problem, I believe, so if you finish it out, you could do this on your own. You should get a critical point of x, y equal to 2, 2. I say not very confidently. 8, 16, 16. No, sorry. No, sorry, 4, 4. Yeah, there we go. XY is 4, 4. And then Z should end up being 32 over 16, which is 2. Yeah. So you should get X and Y both being 4 and Z equal to 2. It is worth your while, I think, to actually finish this problem. I certainly plan on doing it on Tuesday, but that's 5 days away. So yeah. So those are 4s, not 2s.